This is Unit 7, Target 4. No, Target 3, distance formula. Sorry, Target 4 was the Pythagorean theorem. Unit 7, Target 3, distance formula. The distance formula is given here inside this blue box. Distance equals the square root of a bunch of stuff. What I want to show you in the video, though, is two things. One, I want to show you how to use the formula, which we'll do on this problem and this problem. And I want to show you where the distance formula comes from. It's going to be something hard to remember unless you really understand or have seen where the formula comes from. So I have a right triangle, and on a graph what we would do is we would normally kind of add up the boxes we see to tell the difference for the sides. So I could add the boxes here and say horizontally from this point on the right to this point on the left there are 7 boxes, and vertically that there are 4 boxes, and I could use the Pythagorean theorem. What I want to show you is that you can do that even if you have numbers that aren't easy to use. Let's say the triangle was in a spot where it was decimal numbers, and so you couldn't really count a number of boxes to figure it out. If I did look at these numbers specifically, though, on the x-axis, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 for the point all the way to the right, and 2 for the point all the way to the left. So 9 minus 2 gives me 7. No matter what the numbers were, I could find a distance by subtracting. Let's say each one of these lines on the bottom of the screen, or on the x-axis, had a scale of 2. So this was 2, 4, 6, 8, etc. This number would be 4. If I kept going, 2, 4, 6, 8, 10, 12, 14, 16, 18, this number on the right would be 18. Well, the length of that red segment then, from 4 to 18, is going to be 14 units long. I can get that by simply subtracting. 18 minus 4 gives me 14. And the first one, it was 9 minus 2. 9 minus 2 gave me 7. So I can always get that horizontal part that goes with the x by taking the two different x numbers and subtracting them. Likewise, if I knew the y values, if I knew that this y value was 2 and the higher y value was 6, I can count on the graph and see that's 4, or I could say 6 minus 2 is equal to 4. The point of all of that is to get you to see that to find the horizontal and the vertical components of the triangle, or the flat and the up and down parts of the triangle, we can get those numbers by subtracting the numbers we have, by subtracting the x's and subtracting the y's. We can generalize that to any x and any y instead of these specific numbers. So if we had a point here, and we called this point x1, y1, and we had a point here on the top right, and we called that point x2, y2. Then technically this point in the bottom right would have the same x-coordinate as the pink point, x2, that would be on the x-axis, and the same y-coordinate as the blue point, y1, just to list everything out. And I might wind up erasing that to make it easier to see, but essentially, to find this bottom length, I'm going to take x2 minus x1, because those are my two x's. So this is x sub 2 minus x sub 1. That's the same thing I did with the numbers before, but now I'm using letters to show the second x minus the first x. To find this y value on the side, we can see it's 4 boxes, but more generally, it's going to be y2 minus y1. Any of the two y values, again, to find those numbers, 6 minus 2 gave us 4, so y2 minus y1. I'm going to erase some things and leave those there so we can see what we're working with. So using the Pythagorean theorem, I can take my A and my B and my C and set up the Pythagorean theorem. Pythagorean theorem says a squared plus b squared equals c squared, or the two legs squared add together to give you the square of the hypotenuse. So this A is going to be x sub 2 minus x sub 1 squared plus b, y sub 2 minus y sub 1 squared. Ran out of space there, so I'm going to say equals c squared. So a squared plus b squared equals c squared. Or if I wanted to say that this was the distance, I could call that a d for distance squared. So c from the right Pythagorean theorem, or d for distance. And then to solve it, I need to get d, not just d squared. So I would take a square root on the left and a square root on the right. And so that results in d equals the square root of x minus x squared plus y minus y squared. And so it came from the Pythagorean theorem using these general numbers. You find the difference in the x's and square it, and the difference in the y's and square it. I think for time, I'm just going to skip the example here. We did do it in class, so you can look at it, and I'm going to do this decimal example because the video is starting to get long. So I can plug in numbers for my formula. I can write down x sub 1, y sub 1, x2, and y2. And you can plug into the formula, but you can also think through what the formula is saying. We're taking the square root because we had the square root of a squared plus b squared when we did the Pythagorean theorem. We have x2 and x1. So the difference in the x's is negative 3 minus 1.3. We're squaring it because it's a squared for the Pythagorean theorem. For the y values, negative 7.1 minus negative 2 squared. A squared plus b squared equals c squared. So our x's squared, the difference in the y's squared, added together will give us our distance squared. Now we're going to work that out. So negative 3 minus 1.3 is negative 4.3 squared. Negative 7.1 minus a negative 2 is negative 5.1 squared. I put the negatives inside parentheses so that when I type them in my calculator, I do get a positive number. A number squared is always going to be positive unless it's 0. So 4.3 or negative 4.3 squared is 18.49. 5.1 or negative 5.1 squared is 26.01. If I add those two together, I get 44.5. And so that's exact as I can get. I'm not going to be able to simplify a decimal. I can type in the square root of 44.5 since it's already as a decimal, and that will simplify to approximately 6.671. So that's an example of the distance formula being worked out with decimals.